visible?
Yes, but I think you can change to the normal presentation, not from the presenter view. Is it possible to change that?
Okay. Sorry.
Yes.
Now okay?
It's okay. Yes. I think it's
Okay.
should be okay.
So
Yes. Okay.
okay. Okay, so hello everyone. I am Ratha from Akita University, Japan. I am going to talk about minimizing optical magnetic measurement. It's not moving. Sorry, 1 second.
I think the
Is it,
mode.
is it okay?
Oh, can you?
My cursor is moving.
It moves. Yes.
Okay. I'm sorry. I'll start now. Okay, so I'm sorry for the inconvenience. So I'm going to talk about the minimizing magnetic property in bismuth ferrite multiferroic thin films during microfabrications. So before going to the work, I would like to say about the motivation behind the work. As we know, in the case of magnetic memory devices, for the example, in the case of our extract memory, we write data by using spin current. In the case of STT RAM also, we write data by using spin current. Also in the case of magnetic optical devices, for example, special optical modulator, here also we write data by using spin current. If we think about magnetic sensor devices, here the output signal is not so high. So in all the cases we are having some problem, that is output signal is not so high. Otherwise this is consuming very high amount of energy. To solve this problem we should have some new ideas. So let's think about the multiferroic material. As we know, these are the material and it shows more than one ferroic properties in one phase, and these are mostly perovskite structure. And I'll be considering bismuth ferrite because it has perovskite structure, and additionally it has spontaneization polarization along diagonal, and it shows Curie temperature, Nil temperature very high, that is room temperature. So I am not worried for the temperature. But there is one problem, it shows antiferromagnetic G-type structure, which is really a problem for this type of device applications. But we come up with some papers, they are substituting few elements and they could enhance the magnetic property as well as electric property. You can see these hysteresis loops are the signatures of the enhanced magnetic property and electric property. So now I will say how we can use this material in devices. You can see the pink part represents the multiferroic thin films, and this is electrodes. As I said, the ferroelectric property and ferromagnetic property is interlinked. That is, ferroelectric vector and ferromagnetic vector has a good relationships inside the multiferroic thin films. So if I can switch the ferroelectric vector, then the magnetic vector will be changed immediately, which I can achieve by voltage change. So as a result, I can achieve very low writing current, that is electric consumption is very low, and it causes a very simple element structure that also causes a low cost, and there is no use of any noble material, that is also very low cost. But for these three types of applications, I should one thing, for memory devices I need high saturation magnetization and high perpendicular anisotropy. For optical devices, high curve rotational angle and high perpendicular anisotropy. For sensor devices, I need low coercivity and high saturation magnetization. If I can achieve these properties in these materials, then I can say that these materials are better for the application point of view. Okay, so we fabricated our thin films by using pulsed DC reactive sputtering with very high frequency plasma irradiations. This is similar with normal sputtering method, so I'm not going much into this process. But I would like to say here, in our machine there is a very special thing, that is VHF plasma, which really helps us to increase the crystallization. As a result, we are able to increase the magnetic property and electric property. So you can see in our previous result, we substituted a barium in bismuth ferrite and we could achieve the magnetic property that is very highly enhanced, and you can see the signature, the hysteresis loop, and one thing I said here, the crystallization will increase, and this is fabricated by RF sputter, and this is by pulse DC sputter. You can see in the case of pulse DC, the magnetic property is really very high, but there is one problem in this material. that it showed very low Curie temperature around 350. And before I said I need perpendicular magnetic anisotropy, but in this material I could achieve in plane magnetic anisotropy, which is not sufficient from application point of view. In my work, I substituted many lanthanoids and cobalt at a particular percentage. So I tried lanthanum, neodymium, samarium, gadolinium, dysprosium, erbium, europium at different compositions and different conditions. Then I found in the case of a neodymium substituted bismuth ferrite, the saturation magnetization is very high. Like I said, in the case of high saturation magnetization, I can use in memory devices. In the case of lanthanum substitution bismuth ferrite, I could achieve very high core rotational angle that is good for the optical device. And in the case of europium substituted bismuth ferrite, it showed very low coercivity that is good for the magnetic device application. As I said before, I need these three characteristics for the application point of view. So luckily, I could find these three applications. So as I said, I need perpendicular magnetic anisotropy. So we studied CF Stoner-Wolfert single domain particle to ensure the perpendicular magnetic anisotropy. By changing the angle, we achieved maximum coercivity at 90 degree, and hence we said that these materials are showing perpendicular magnetic anisotropy. Okay, so now I will be saying I could fabricate many three elements. So are they really suitable for the device applications? That answer I can give from if their domain size is very less and if their Curie temperature is very high. In the second part, as we know, to fabricate micro devices, we have to undergo microfabrication, and microfabrication is carried out by etching, and that causes magnetic damage. So I'll be investigating the suitable magnetic property or suitable etching conditions which will give very low magnetic damage. Okay, so as I said, I checked the grain size and domain size in these three thin films, and I found the grain size is around 50 to 100 nanometer and the domain size is around 150 nanometer. That is also suitable for the nano device applications. In the second thing that I measured the Curie temperature in all the thin films, the Curie temperature is around 450 degrees Celsius. So before I found 350 and I said that is not so high, and here we could enhance little more, that is 450 degrees Celsius, and this is better for the device applications. In the second part, as I said, I will be showing the best way to etching that will give very less magnetic damage. So to study that, we fabricated micro dots on our thin films of 3 micrometer. Then so here I will say one point, these dots are covered with resist. So when I will expose these thin films to etching, the dot area will be covered from etching, that is no etching, and out of dot area is etched. That means I have to now see the magnetic property changes between on the dot and out of dot. If the property is very highly changed, that I can say that is giving magnetic damage. So I choose two types of thin films. Then I fabricated one with reactive ion etching, that is, this is on dot area, this is out of dot area. In the case of a dry etching also, I am comparing on dot area and out of dot area. This is the phase difference. Here I did not find any phase difference. Then I cannot say that there is no magnetic damage. So to confirm that, I carried out few more characterizations. Like you can see here, this is the domain study, and here the grain size and domain size is not affected when the etching is performed by reactive ion etching. But you can see in the case of a dry etching, there is an increment in the domain size that can cause magnetic damage. That means dry etching is causing magnetic damage with respect to reactive ion etching. To confirm it again, we studied the change in coercivity by micro-mock measurement system. By changing, you can see this center area is the dot center, and out of area is etched area. So when I'm taking my laser from center to the out of dot area, in the case of a dry etching, this green one, it's changing drastically. That means here also we found in the case of a dry etching, the magnetic damage is high with respect to the reactive ion etching. As I said, one thing, dry etching is not good with respect to reactive ion etching. Now I'll be checking reactive ion etching, but what type of reactive ion etching? What is the better reactive ion gas? Okay, so I consider two gas. One is CHF3 in the presence of oxygen, and another is only CHF3 in the absence of oxygen. You can see in the case of presence of oxygen, there is almost no change in the grain size and domain size. But in the case of absence of oxygen, there is an increment in the grain size as well as domain size. That means if I will carry out the etching in the presence of oxygen, that will give you very less magnetic damage. So here is the same coercivity test by micromove measure-based system. As I said, in the case of oxygen presence, I'm not getting much magnetic damage, and in the case of only CHF3, this is also increasing drastically. That means CHF3 is not good for the etching process. So to confirm that, we found that there is a beautiful role of oxygen which cause all these things. To confirm that, so what we did, this is our base material. We did XPS study. This is our best material, and this is in the presence of oxygen. This is without oxygen. You can see there is a beautiful change in the oxygen vacancy. When the material is not etched, that is 27% of oxygen vacancy found. When we etch the material in the presence of oxygen, 60% oxygen vacancy we found, but there is no oxygen, then the oxygen vacancy also increased. And here also we confirmed that in the presence of oxygen, the magnetic damage is very less. So if I discuss my second part of the work, which is really interesting, so we found an increase in the grain size, domain size, coercivity in the presence of CHF3. So if we introduced oxygen with CHF3, we could reduce all these things, and we could find an optimized magnetic property. That is no change in the magnetic property even after the microfabrication. That means RI is better than dry etching. So this is the summary of my work. In the future, we are trying to optimize the dry etching because dry etching is not yet optimized. So thank you very much for your presence, and I would like to thank to my collaborator from NIMS and Osaka University. Thank you.
Okay, thank you so much for the report. Is there any question from our attendees? Okay. I have no question. Is it possible to move on to the next speaker?
Okay.
Okay,
Thank you.
yes. Thank you so